Alright, gang, here we go. Chem 2, Unit 6. We're talking about bond enthalpies. Alright, so we've kind of already talked about this in the previous units. So this should be mostly review. Okay, bond enthalpy, okay, is the enthalpy associated with breaking 1 mole of a particular bond in a gaseous substance. So that's how it's defined. Okay, a couple of things to remember is that we're always talking about 1 mole, okay, and we're assuming that it's gas. All right, so if we got these guys and we're bringing them up, how much energy does it take to break those bonds? Okay, bond enthalpy is always positive because it's an endothermic process. Okay, remember endothermic energy is coming in, and it's positive because bonds don't want to be broken. So in order to break them, bonds form because they're low in energy state. Okay, so in order to break that bond, you have to make those atoms or elements to be in different or into a higher energy state. So you have to kind of pay them off a little bit. So by giving them more energy, that's kind of how I think about it. So anyway, so breaking bonds is always an endothermic process. Okay, so when you break that bond, you are putting energy into the system, and then when bonds are formed, okay, energy gets released. All right. So essentially, that's what's essentially when you learned about ATP in biology, it probably what your biology teacher said was that, well, breaking ATP or using ATP gives you energy. You're breaking that bond and you get energy out of the bond, right? And that's not quite how it works. You're not getting energy out of the bond that you're breaking. What you're doing is you're putting a little bit of energy into breaking that ATP bond, and then you're getting a lot of energy in return when it forms the new ADP molecule. Okay, so you're actually getting energy because it's formed that new bond, not because you broke the old bond. Okay, so anyway, it's a good investment. You have to put a little bit of energy to make it occur, and then you get a lot of energy back. All right, so anyway, so the greater the bond enthalpy, the stronger the bond, because remember, the more energy you had to put in, the stronger that bond was, so therefore the greater the bond enthalpy, etc., etc. Okay, so here's some average bond enthalpies. So carbon hydrogen is 413, carbon is 348, and you can kind of see this. One interesting thing is you can notice that, and this should be common sense, you should know this by now, double and triple bonds are stronger than single bonds. Okay, so like here you've got a carbon-carbon bond here is 614 versus carbon single bond is 348. So it's almost twice as strong. Not quite though. Okay. Here we go. Carbon-oxygen single bond 358. Okay. Carbon-oxygen double bond is almost 800. So it is more than double. Okay. So, and you can kind of look at this. Maybe you can see other patterns depending upon ionic sizes. All right. Electronegativities, maybe take some ganders at some of those. All right, so bond enthalpies and enthalpies of reaction. So essentially, how can we use these bond enthalpies, okay, in order to calculate the enthalpy of a reaction? Okay, so essentially all we have to do is kind of the same thing we've been doing so far, is just add them all up and subtract them, right? So it's always bonds broken minus bonds formed, okay? Bonds broken, so add up all the bonds that are broken and then subtract out all the bonds that are formed, okay? And this is a good estimation of our enthalpy of reaction, all right? So here's a reaction of methane reacting with chlorine gas, okay? And you get this CH3Cl, right, and HCl and hydrochloric acid. This is the reaction that occurs in order to form hydrochloric acid. All right. So anyway, so it's a mildly exothermic process. Okay, and you've got chlorine gas with CH2, and then you break up the bonds that are broken, right, and then you form these new bonds over here. All right. And you can add it, you go bonds broken minus the bonds formed, and you get the enthalpy of the reaction, that difference. Okay. So we'll just do a practice problem. Oops. We'll do this practice problem here. So use average bond enthalpies to estimate delta H reaction for the combustion of ethanol. Okay, so ethanol, and so we've got, so we're just going to write out the balanced chemical equation real quick just to help us out. C2H, 1, 2, 3, 4, 5, 6, 6, okay, O, plus O2 goes to CO2 plus H2O. Okay, so we got to balance this. So we got 2 carbons here. We need 2 carbons here. We got 6 hydrogens, so we'll put a 3 here. And we got 4 oxygens, 3 oxygens, so that's 7 oxygens on the right-hand side. Well, that's stupid. So that means we need 7 halves oxygen over here. Okay, 7 halves oxygen. So then we will multiply everything by 2, so we get a 2 there. 2, 4, 6, so 7. Okay, 7, 4, and 6. And we should be all balanced. Let's just double check. So 4 carbons, 12 hydrogens, 12 hydrogens, 14, 16 oxygens, okay, and 8 plus 6 is 14. What did I screw up? Did I do it wrong before? Oh, I totally did it wrong before. You guys should have stopped me. This is embarrassing. Okay, so if I just... Oh my gosh. Alright, so if we did 2 carbons here. See, even when you've been doing these things forever, like, you can still make mistakes. So there's 4 oxygens here, 7, and then if we put a 3 there, and then now we've got 7. Ugh, that was stupid. Alright, here we go. So we want to do bonds broken minus bonds formed. We got to think about what these guys look like. So oxygen is a double bonded compound like this, right? So we got 2 oxygen, we got 3 of those, right? 3 of those guys, 1 of those guys. Carbon dioxide, so we got 2, and this guy looks like this, right? Aren't you glad we practiced all those structures? All right, and then plus 3 times our water, which is a hydrogen, oxygen, hydrogen, okay? So bonds broken minus bond form, okay? So bonds broken, so we have C in our ethanol here. We've got 1, 2, 3, 4, 5 CH bonds, okay? 5 times CH bonds, okay? CH single bonds, okay? Plus, okay, so these are all our bonds broken, plus 1 carbon-oxygen bond, plus 1 oxygen-hydrogen bond, plus 1 carbon-carbon bond, carbon-carbon bond. All right, did I forget any? All right, so that's our ethanol. And then we also had 3 oxygen double bonds. Okay, so those are all the bonds that are broken. Okay, and then now we're going to subtract out all the bonds that are formed. Okay, so let's see what's formed. So we've got 2 sets of 2 CO double bonds. So we're going to have to multiply that by 2 twice, right? Because each carbon dioxide has 2 of those. All right, so 2 of those. And then we're going to add in, same idea here, we have 3 waters, but each water has 2 OH bonds. Okay. Now sometimes you can get kind of lucky when you're looking at these and you can cancel things out. But we really, all we could cancel out is one of these OH bonds, but I don't think it's going to help us that much, so we'll just ignore it. All right, so now we got to look at that table. Okay, so we'll say 5 times our CH bonds. So now we go look at this table here. So CH is 413. All right, so CH 413. Okay, plus our carbon oxygen single bond. Okay, 358. Plus our oxygen hydrogen single bond, 463. Plus our carbon-carbon single bond, 348. Okay, 348. Plus 3 times our oxygen-oxygen double bond, 495. All right, now we do the same thing, but now with our products, we've got 2 times our carbon-oxygen double bond, 799. Parentheses, plus 3 times 2 times our OH bond, which we had over there, which was our 463. All right, so now, gotta make sure we don't put it in our calculator right. So 5 times 413 plus 358 plus 463 plus 348 plus 3 times 495. Okay. So our bond's broken. It's going to take 4,719 kilojoules. All right. We're going to subtract out all of the bonds that are formed. So 2 times 2 times 799. plus 6 times 463. So 59, 974. Oh, shoot. You know what? I just realized that you probably can't see this all around my head. So we'll do this up here. So, all right. So our bond's broken, okay, is equal to 4,000. So this is equal to 4,719 kilojoules, okay, minus 5,974 kilojoules, all right? So then when we subtract those 4,719 minus 5,974, we get negative 1,255 kilojoules is our delta H of reaction, all right? So just one more way of calculating the delta H of reaction that's going on, all right? A couple more things we need to talk about here. Okay, energy in foods. Okay, so energy released when 1 gram of food is combusted is known as its fuel value. Okay, and here's a table with a bunch of different things you can look at. Okay, so carbohydrates, okay, are all carbohydrates, and they provide 17 kilojoules per gram. Okay, so they have a lot of energy per gram, okay, or 4 big C calories per gram. Okay, notice that a kilocalorie is equal to a big C calorie. All right, and then fats are all fats. Okay, they have 38 kilojoules per gram and 9 kilocalories per gram. Proteins are all protein, 17 and 4. Okay, so apples are a mix of all three of these. They're 13% carbohydrate, 5% protein, and 0.5% fat and 0.4% protein, and the rest would be something else, not one of these three things. Okay, and so apples give you about 2.5 kilojoules per gram, or about 0.59 kilocalories per gram. Beer, okay, it's almost all carbohydrates, well, and then 0.3 proteins, okay, and then bread is a lot of carbs, okay, and then fats and proteins as well. And so you can see fuel value, like bread gives you a lot of energy, which is the reason lots of people eat bread, and why bread was like a huge sustaining portion in almost every developing society. Okay, and there's some more. Okay, look how much fat peanuts have. So fatty, so fatty. And that's kind of nuts in general. It's kind of nuts. All right, so energy in foods, most of the energy we care about, okay, that's worth mentioning, comes from either carbohydrates, fats, or proteins. Carbohydrates, all right, so there's your general how we calculate this would be sugar, okay, C6H12O6, glucose, okay, and so this is the delta H of reaction of combusting this carbohydrate. And then fats, fats are combusted in your body, pretty scary, and look how much more energy like one fat gives off. But notice that that's probably because there's way more bonds being broken and bonds being formed. You're forming 114 molecules of CO2 for every 2 molecules of fat that are being burned, whereas with carbohydrates you're only burning 6. Okay, big difference. Proteins, okay, produce 17 kilojoules per gram, okay, and their chemical reaction is not the same as what goes on in a calorimeter, so you can't use a calorimeter in order to calculate those values. You just kind of have to, we're not going to go into it in this class, we're just going to assume that that's correct, okay. So, and then also energy and fuels, just a real brief thing here, okay. Most of the energy, at least right now, most of the energy that we use comes from fossil fuels, either natural gas, petroleum, or coal, okay. But there's still growing, renewable energy is growing a lot, okay. And the nuclear energy is kind of stagnating, if not going down. It's got kind of a bad rap and stuff like that. Okay, fuel values. You can kind of see the fuel values for these guys. It's essentially the same thing as calculating for the energy in food that we just talked about. And you can see like hydrogen produces a whole lot of energy per gram, right? Compared to some of these other things, like burning just straight wood doesn't really help you very much. But once you're burning coal, like it produces a lot more. Okay, crude oil, well, gasoline, natural gas. So, you know, there's a reason that burning these things gives off lots of energy, because they've got high fuel values. Okay, nuclear fission produces about 8.6% of the U.S. energy needs. Okay, renewable energy sources like solar, wind, geothermal, hydroelectric, biomass sources produce 9.9% of the U.S. energy needs. Okay, so biomass sources, this would be places like, or this would be like at, I know that KU campus, I think, I know it was a couple years ago. I haven't checked on what they're doing now, but they have a huge renewable energy push in their engineering department, chemical engineering department, and they've got giant vats of algae and fungus. I think primarily algae that are producing oxygen and other waste from the algae that they're actually using to run the buses that bus students around campus. Okay. And that's it. That's all we're going to do with energy and food. And so that wraps up Unit 6. Congratulations. You made it through another unit. I'm very proud of you. Do your practice problems. Let me know if you have